Hello, this is Miss Moore, and today during chemistry we're going to discuss Lewis-Dot structures. Today's essential question: how are Lewis-Dot structures used to show covalent bonding? You will need your periodic table handy for today's lecture. Okay. We need to start with a review of ions, ionic compounds, and ionic bonds, because Lewis-Dot structure is actually a preview, or step one, of a different kind of bond, which is the covalent bond. All right, so hopefully you remember, atoms become ions to achieve noble gas configuration, right? To be like something S2, something P6. And then after atoms become ions, they form ionic bonds. They hook up with somebody of the opposite charge, making the atoms neutral, or the ions neutral. Remember, they want to be noble and neutral. And ionic bonds are formed between metal cations and non-metal anions. Or there could be a polyatomic ion thrown in there, a polyatomic cation, or a polyatomic anion. And the ionic bond is the force that holds ions together to form the compound. And this force, this magical force that holds them together, is the attraction of the negative and positive ions. Pretty basic. I think you guys are pretty comfortable with ionic bonds. So now we're going to talk about covalent or molecular bonds. So a different way for atoms to achieve a noble gas configuration, remember that's the goal, that's what all atoms do. They want to be like the noble gases. So whatever they do, they're trying to be like the noble gases. So one way to do that is to form ions and then ionic bonds. Another way is through the formation of covalent bonds. So covalent compounds are formed when elements share electrons. Share electrons. That's very different. And the bond in which electrons are shared between two atoms is a covalent bond. Okay, so with an ionic bond, you've got the situation where one atom steals an electron from another, leaving one positive, one negative, right? In this case, we've got a covalent compound. What happens is two atoms are trying to hold on to the same electron. So they're sharing one electron, okay? And that, again, is a covalent bond. And covalent bonds are formed between two non-metals. So like chlorine and chlorine, oxygen and chlorine, sulfur and oxygen, two nonmetals. Remember the jaggedy line? Two guys that are on the right side of the jaggedy line. Types of covalent bond. We've got single bonds, double bonds, and triple bonds. So for now, we'll get the definitions. It'll make a lot more sense after you actually see a Lewis-Dot structure. So a single bond is a bond in which two atoms share one pair of electrons between them. One pair. So each atom is donating or sharing an electron with the other one. So they're each sharing one electron, ends up being a pair of electrons. A double bond is a bond in which two atoms share two pairs of electrons between them. So they're sharing a total of four electrons. And a triple bond, I'm sure you're getting the routine here. A triple bond is a bond in which two atoms share three pairs of electrons. So that's a total of 6 electrons. Right? So for a single bond, you're sharing a total of 2 electrons. Double bond is a total of 4. And triple bond is a total of, not 5, let's try that again, is a total of 6. All right, now we're getting to it. Lewis-Electron-Dot structure. That's the full name. You can call it Lewis-Electron-Dot structure. You can call it Lewis-Dot structure, Lewis-Dot, electron-dot, electron-dot structure. I usually call it Lewis-Dot. All right, Lewis-Dot structure are used to determine the number of electrons shared in a covalent bond. It's kind of cool. It's like a little picture, a little model that you move around like a puzzle. And Lewis-Dot, what you're doing is you're using the outermost electrons, the valence electrons, that are involved in bonding, whether we're talking about covalent or ionic. And Lewis-Dot structures represent the valence electrons in a molecule or in an atom to start out with. Okay, those are the guys involved in bonding. Okay, so drawing Lewis-Dot structures for a single atom. You start by writing the atom symbol. Then you determine the number of valence electrons. The valence electrons are going to be written as little dots around the atom symbol. And remember that it's only the s and p orbitals that can be valence electrons. So there are 4 possible orbitals for valence electrons, right? You've got the orbital in the s and then the 3 orbitals in the p. So you have a total of 4 possible orbitals, which means you can have a total, the maximum number of valence electrons is 8. And when you're drawing Lewis-Dot structures, you want to think of each side of the atom symbol as representing 1 orbital. Okay, so before we go through the examples, let me draw a little picture for you. So we'll take some atom X. We don't care what atom it is. Okay, and you want to imagine that there's an orbital here, an orbital here, here, and here. Okay, so think of those boxes just like when we're doing orbital diagrams as orbitals. Okay, and how many electrons can fit in an orbital? 2, a maximum of 2. And think about how you fill them up. Right, you'd put 1 in each first. So this is called Lewis-Dot structure. So we're going to use dots. But when you fill them up, you fill 1 electron in each orbital, just like you would do for orbital diagram before you go back and put in the other ones. Okay, so those dots are representing the electrons. All right, let's try a few of these. Start with carbon. And if you recall, the first thing we need to do is know the number of valence electrons. So the electron configuration for carbon is 1s2, 2s2, 2p2. And the definition of valence electrons are the electrons in the outermost energy level. The outermost energy level is energy level 2 in this case. So those are carbon's valence electrons, and there are, how many valence electrons there? There are 4. All right, so when you do this, you write carbon, and then you just place the 4 electrons around the symbol in the imaginary orbitals. So 1 in each location. So 1, 2, 3, 4. And that is the Lewis-Dot structure for carbon. All right, let's try neon. 1s2, 2s2, 2p6. And neon's valence electrons are 2s2 and 2p6. That is a total of 8 valence electrons. So neon has the maximum number of valence electrons. So neon, when we do the orbital diagram, we'll start. It doesn't really matter where you start putting the electrons, just as long as you put 1 in each imaginary orbital first. Okay, and now we have 4, so now we need 4 more. We can go back and pair them up. And that is the orbital diagram for neon. All right, I suggest you hit pause and you try to do the Lewis-Dot structure. I think I said orbital diagram for neon, sorry, the Lewis-Dot structure for neon. Anyway, I suggest you hit pause and try to do the Lewis-Dot structure for nitrogen by yourself, and then hit play and see if you could do it. All right, so the electron configuration for nitrogen is 1s2, 2s2, 2p3. There are his valence electrons, 2s2, 2p3. So he has 5 valence electrons. So Lewis-Dot, 1, 2, 3, 4, and then we get to pair up 1. It doesn't really matter. I usually pair up the top. Doesn't really matter. And that would be the Lewis-Dot structure for nitrogen. Okay, so now we know how to write the Lewis-Dot structure for a single atom. That's just the beginning. That's the real thing we want to do is draw Lewis-Dot structures for covalent compounds. And remember, a covalent compound is a compound in which the atoms are sharing electrons. Okay, so the first thing you want to do is draw the Lewis-Dot structures for each atom in the compound. So I guess we need an example here. How about OF2? Okay, so O is 1s2, 2s2, 2p4. Valence. He has 6 valence electrons. So the Lewis-Dot structure for oxygen will be 1, 2, 3, 4. And then again, you need to pair up 2. Top and bottom works for me. That's up to you. And then we've got fluorine, which is 1s2, 2s2, 2p5. Valence electrons there are 7. So fluorine, Lewis-Dot, 1, 2, 3, 4, 5, 6, 7. And we have 2 of them. There we go. All right, so we have the Lewis-Dot structures for each atom in the compound. Next, determine the total number of valence electrons in the compound. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18. We have 20 valence electrons. Okay, next we're going to arrange the atom symbols, the Lewis-Dot structures of the atoms, to show how the atoms will bond. Okay, and really important here is you need to start with the atom that needs the most electrons. That will make life easier, and it normally works. Okay, so what you need to keep in mind is that what's the goal of each atom? Each atom wants 8 valence electrons, just like the noble gas. But this time, instead of stealing, they're going to share. Okay, so let's see who needs the most. We've got oxygen, who has a total of 6 electrons, but he needs 8, so he needs 2 more. And each of the fluorines have 7 electrons, so they need 1 more. So oxygen needs the most, so we'll start with him. We'll draw him in the middle, and we'll put his valence electrons in. And, all right, so let's look at this. Where do we need more electrons? Remember, we want 2 in each of the imaginary orbitals, so we need an electron here and here. And if we look at the fluorines, we need 1 here and here. So can you imagine, think of these as puzzle pieces. What if I were to take this fluorine right here, pick him up, and move him down next to the oxygen? Okay, just draw him just again. Can they share these 2 electrons there? Yeah, totally. Then what we're going to have to do with this fluorine, could we do the same thing? Keeping in mind that it doesn't matter exactly where the electrons are. So what I'm going to do is rearrange, okay? I'm going to take one of the electrons over on this side and move it so he'll bond better. So we still have our 7 electrons. He needs another one here, so they can share right there. So now the next step is you need to make sure there are 8 dots around each atom, except for hydrogen. If you remember hydrogen, he'll be full if he only has 2 dots. So let's do that, remembering that they're sharing. So if we start by looking at fluorine, the first fluorine, those are his 8 dots, right? 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now if we look at oxygen, he has 2, 4, 6, 8. And lastly, we look at the fluorine. He has a total of 8. So there are indeed 8 dots around each atom. So they've all got noble gas electron configuration. So the next thing we need to do is compare the number of valence electrons used in the structure with the number available in step 2. So let's look back at step 2 and see how many valence electrons we had. And it looks like we had 20 available. So let's go back and check how many we have now. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we still have our 20 electrons. But we've made each of the atoms happy without any stealing going on. What they did instead is share electrons. All right, so the very last step is to change each pair of dots that represent a shared pair of electrons to a single dash. So all that pink stuff we're going to turn into a dash. So I'm going to start by writing my F and O and F and connect the dots. Oh, you know what? I'll do that in pink to make it more obvious. Okay? So this represents, that's 2 electrons, or 1 pair of electrons. And then we just fill in. Let's put all our other valence electrons back. And that is the Lewis-Dot structure for OF2. All right, let's try one more practice problem. Let's do SiS2. Okay, so if we want to draw the Lewis-Dot structure for the compound SiS2, the first thing we need to do is draw the Lewis-Dot structure for Si and for S2 for S. And to draw the Lewis-Dot structure for each of those, we need to know the number of valence electrons. So if we start with silicon, silicon is 1s2, 2s2, 2p6, 3s2, 3p2. So his valence electrons are there. He's a total of 4. So he'll be Si with 4 valence electrons. Okay, we try sulfur. Sulfur's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p4. So his valence electrons are 3s2, 3p4. He has a total of 6 valence electrons. So our sulfurs, I'll try that again. Our sulfurs are going to have 1, 2, 3, 4. After that, you can decide where you want to pair. I'm going to put one on the top and one on the bottom. And I guess we should draw another sulfur. 1, 2, 3, 4. All right. So let's figure out where we need more electrons. Remember, they want 8 around each. They want them to be paired up. So this guy needs 1, 2, 3, 4. This guy needs 1, 2. And this guy needs 1, 2. So silicon needs the most. So we'll start with silicon. So we'll bring silicon down here. And now, where are we going to put these sulfurs? All right, so now when we place the sulfurs, it looks a lot more difficult, but honestly, start with the obvious and we'll go from there. So it looks to me like we could put, like we did with the fluorines, we could put 1 sulfur on either side. So we could have our sulfurs on either side, and those two can hook up. Unfortunately, nobody's happy yet. But do you remember, it doesn't really matter which invisible orbitals would put the electrons. So what if I did a little changing here? What if I put the paired electrons here and the lone one there? Could he then share there? And I could do the same thing on the other side. We still have the right number of electrons, right? We just rearranged them. So now let's look and see if they have the right number of electrons. So if we look at sulfur, Can you see that? 2, 4, 6, 8. He has 8 electrons. And if we look at silicon, he's in that area there. 2, 4, 6, 8. He has 8 electrons. And if we look at the last sulfur, I didn't quite box those in. 2, 4, 6, 7, 8. Bring this one in too. There you go. Okay? So they all have 8 electrons. So now we need to rewrite this mess. So we have S, Si, and S. Now what we're going to do is we're going to take those 2 pink lines and kind of just shift them around right there. See what I did there? And then we can put the rest of the valence electrons. So if you count again, we should have 8 electrons around each, keeping in mind, it's a little easier to count on this one. If you look at this, remember each line is worth 2 electrons, right? So 2, 4, 6, 8. 2, 4, 6, 8. And 2, 4, 6, 8. So we did it. Now, any idea what that's called? That would be our double bond. All right, that's it for today.